Hi again, welcome back to the second video. We ended the first video looking at some examples of bias that were created because of how the data were collected. We're now going to look at variability. This example is on stock prices. In basic terms, a stock price is the amount at which someone is willing to buy and someone is willing to sell company shares at any given time. And stock prices fluctuate in both the short and long term. My colleague went to his data source and he randomly chose some companies and he extracted data on their stock prices for each of 365 consecutive days. On the y-axis on any of these plots, we've got the standardized price, and on the x-axis, we go from day 0 to 365. He then went and completely separately generated completely fake stock prices, and I'll explain to you how he did that. He chose a price for day 0, consistent with the range of the data, randomly, and then to go from the stock price on any given day to the stock price the next day, he added a random fluctuation. This fluctuation followed a normal distribution, so values closer to 0 are more likely, and larger values, positive or negative, are less likely. And he chose a distribution so that it lies almost entirely between -3 and 3. So on the slide, there's a mixture of two types of data, the real stock prices and the fake ones. And the question I'm going to pose is, which would you guess are real and which would you guess are fake, and why? I'll also tell you that at least one of the stock prices is real and at least one is fake. So I'm just going to step out of sight for half a minute to give you some time to think about it. So some of the questions you might be thinking about are, what would a real stock price look like? Or what would a fake stock price look like? If it's real, what do we expect to see over the span of a year? Do we expect to see a trend, some sort of seasonality, some sort of irregular cycle? Would the fluctuation on any given day be related to the fluctuation on the previous day? What would cause an increase or decrease in stock prices, and how big would we expect these to be? So I'll give you just a little bit more time before we keep going. If you'd like a little bit more time, please just hit pause on the video. So on the slide, there is one real stock price. The real stock price is the second one. 1, 3, and 4 are all fake. I'm hoping through doing this exercise, two challenges arose. The first is that it can be really difficult to distinguish noise from what is real or underlying signal. The second is that as humans, we are hardwired to make discoveries, to find explanations for what we see. So, for example, some might be surprised that the third stock price is fake. There are a few consecutive days where the price generally goes down and a few days where the price generally goes up. And one might be surprised by this given how the fluctuations were generated, where it's randomly a downward or upward fluctuation. And we might have even come up with an explanation for this. For example, maybe the CEO made a controversial statement and prices went down, and at some stage later he retracted these. We might also be surprised that the second stock price is actually the real one because of the trend we see. Stock prices are extremely volatile in the short term, and it's generally only in the longer term that we see trends. Continuing this example, here are 1,000 random stock prices generated by the same process, but all starting at 100. So because of how the fluctuations occur, we might expect that if we start near 100, we should end near 100. But looking at this plot, we can see there are actually quite a large number of stock prices that end up fairly far away from 100. Given that there are so many processes that happen all the time in the real world that we might collect data on, there is a probably more than expected chance of actually seeing interesting patterns that are simply just noise. This example continues the theme of variability and the impact it may have. Here we're looking at the impact of variability on how we interpret hypothesis tests. Hypothesis tests are going to be discussed in more detail in one of the upcoming lectures, so I don't provide the technical details. In summary, we might have a hypothesis, we then collect data, and we try to understand the strength of evidence in our data in relation to our hypothesis. However, every time we do a hypothesis test, there is a chance that we're going to find the wrong answer. And this is because there's always going to be variability. In this example, somebody claims that jelly beans cause acne. The scientists are sent to investigate, they do a hypothesis test and they find no evidence of a link. And this is indicated by the large p-value. Instead of stopping there, the person claims that it's a certain color that causes acne, and so the scientists are sent to investigate again. They try purple jelly beans and find no evidence, they move on to brown, pink, and they keep going. Just because of the large number of tests that are being done, by chance, we're probably going to find an association at some point. So over here, once they get to green jelly beans, they obtain a low p-value, and they conclude that there's a link between jelly beans, green jelly beans, and acne, and everyone stops eating green jelly beans. It's important to remember that variation is everywhere. So here's a quote by an economist. "When the facts change, sir, I change my mind. What do you do, sir?" Ideally, of course, the facts shouldn't change. However, we are almost never able to directly observe the truth. We collect data which contains variability. When we estimate a parameter, we estimate it using a sample statistic. So for example, we might estimate that HIV prevalence in a population is 15%. This is only an estimate. That's also why we should always report confidence intervals that provide some idea of how certain we are of that estimate and a range of plausible values given our data. Just to end with the equation we've shown before, when we observe something, that observed value consists of three components: the truth that we would like to see, bias, which is your systematic error, and random error or statistical variability, which is what we discussed here. This is the end of the second video. Please join the last one when you're ready. Thank you.